So let's solve our first problem, Halloween treats. And quickly recapping the problem statement, we're given a list of n integers and another integer c, and we want to find a subset of the list which sums up to a multiple of c. If that's impossible, we should tell it's impossible. Okay, so the space of subsets of the list is obviously too large to be considered one by one. It grows exponentially on n. So let's try to find a solution in another smaller space of possibilities. One of them we might consider is the space of prefixes of the list, of the given list. So instead of considering all the ways of choosing elements of the list, we consider only ways in which the elements form a prefix of the list. So let's try that on our second example. So in that example, c equals 3, which means we have to find a group of elements that sum up to a multiple of 3. And the elements we're given are 7, 11, 2, 5, 13, and 17. So the question is, can we find a subset of this list that sums up to a multiple of 3? And for now, let's consider only prefixes. We still don't know if we'll always be able to find a solution in that case, but it might give us some insight on the problem. So if we start with 7, it's obviously not a multiple of 3. So we might add 11, and we get 18, which is a multiple of 3. So in this case, this would be a valid solution. So among the prefixes, we already found a valid solution. Let's try that on the other test case. So in that case, we are given c equals 4, and we're given 5 integers, which are 1, 2, 3, 7, and 5. So let's try doing the same. If we start with 1, we still don't have a multiple of 4. We can add 2, we still don't have a multiple of 4. With 3, we get 6. With 7, we get 13. And with 5, we get 18. So we didn't pass by a multiple of 4 in this process. However, how can we find a way of fixing a prefix? In other words, given a prefix which is not a solution, what do we need to find in order to transform that prefix into a solution? So, of course, if we consider all the possible operations, we could simply say that, oh, we need to find a viable solution, and then remove the elements from that solution, from the prefix, which are not in the solution, and add the ones which are not. But of course, that does not help. So let's try to work with what we have. Given a prefix, another way of transforming that prefix into a viable solution would be to remove from that prefix another subprefix which has the same remainder modulo c as on its sum. Which means that if we have a prefix, let's say, and that the sum of that prefix leaves a remainder of 1 when divided by c, if we can find a smaller prefix which also leaves a remainder of 1, you can see that the difference between them necessarily is a multiple of c, which means that if we take the larger prefix and remove the smallest one, we'll end up with not a prefix anymore. In general, it will be a contiguous subsequence of the original list, but not necessarily a prefix, but a contiguous subsequence which sums up to a multiple of c. Is that always possible? Well, let's see what we need in order to find that. We can see that given two prefixes of any size that have the same remainder modulo c, one is necessarily a subprefix of the other, right? Which means that in order to find a solution through this approach, we only need to find any two prefixes, which have the same remainder modulo c. Alright, but is that always possible? Let's try to think of when would that be impossible to do. So that would be impossible to do if we can't find two prefixes of the list which have the same remainder modulo c. which means that it's impossible to do when all the prefixes have distinct sums modulo c. But how many prefixes are there? Well, counting the empty prefix, which has a size of 0, we have prefixes of sizes from 1 to n, which gives us n plus 1 distinct prefixes. And how many values modulo c are there? Well, there are from 0 to c minus 1, right? So there are in total c distinct values modulo c. But from the problem statement, we know that c is at most n, which means that if we have n prefixes, n plus 1 distinct prefixes, by the pigeonhole principle, at least 2 of them will have the same sum modulo c, which means it's always possible to find a solution using this approach. Let's see how that would work in this case. So, if we start with 1, we can't do anything. We can only remove the empty prefix, which doesn't give us a solution. If we move on to 2, we still can't do anything. The only option we have is to remove 1, but we would have to remove 3. Now, if we add the 3, we have 6, which leaves a remainder of 2, modulo 4. There is no way of removing a prefix with that sum, modulo 4. If we add the 7, then now we get 6 plus 7 equals 13, modulo 4 equals 1. So we have to remove a prefix from this prefix. That leaves a remainder of 1 modulo c. Can we do that? Yes, we can. We can just remove the first element, which would give us this contiguous subsequence, which is a viable solution. You can check that they sum up to 12, which is a multiple of 4. So in this case, this would be the solution we would find using this approach. Now, what would we do in the other test case? Well, starting again, in the other test case, we would just find a trivial solution because the first 2 elements, which are already a prefix, already form a viable solution. So in this case, it would be easier. So, what would be the actual algorithm behind this idea? Obviously, we can't consider all pairs of prefixes because there are at most 100,000 prefixes. So we need a better way of finding that. But that's not too hard because we only have to check if we have already seen a prefix with a given sum, with a given sum modulo c, as we traverse all prefixes. And for that, we can just use a vector. So we can have here, for example, let's try to run the algorithm in this second test case again. So since c equals 4, we have to record whether we have seen a prefix which has a sum of 0, 1, or 2 modulo 4. So 0, 1, 2, or 3 modulo 4. And whenever we find a certain prefix which has a sum which has already been seen, we just found a way of finding a solution to the problem. So what will we store here? We'll store here the size of the first prefix we found, which has this sum corresponding to the row modulo c. So we would start with the prefix consisting of only the first element. It has a sum of 1 modulo c. So we would save here the number 1, indicating that the prefix which has a size of 1 has this sum modulo c. When we add the 2, we get a sum of 3. So we come here and put a 2 here, which is the size of the prefix we found. When we add the 3, we get a 6 in total, which is 2 modulo 4. So we put the 3 here in the 2, in the third row. When we add the 7, then now we get 1 modulo c, right? But we can check that in the table we already have a prefix which has that same sum, modulo c. Which means that we can get a solution by taking the current prefix, which goes up to 7, and removing from it this number of elements, which in this case is 1. So eventually, we know that this will happen because of the pigeonhole principle. And when it does, we basically get the prefix in which it happened and remove from it a certain number of elements, giving us one solution to the problem. So that's the solution to our first problem, Halloween trees.